Good morning. I'm showing 9 o'clock, so we're going to go ahead and get started. My name is Mike DeLacluse. I'm the president of Lesman Instrument Company. I'd like to thank all of you for taking time out of your busy schedule to join us for Fixed Gas Detection 201, Selecting and Installation Tips. Today we have Mike Holmes of Honeywell Analytics presenting, and in the next 45 to 50 minutes, we're going to cover some key topics that include review of gas detection system basics, some applications that require gas detection systems, how to properly select a gas detector. We're going to have a little discussion on controllers versus PLCs, some tips for proper sensor placement, and then we'll have some time for Q&A. Mike has been with Honeywell Analytics for 23 years, supporting a wide array of industry-focused applications, ranging from commercial spaces to light and heavy industrial, semiconductor, and food processing. Currently, Mike covers North America with ties to global support as a subject matter expert. We will be meeting the phone lines. If you have any questions, there is a question tool built into GoToWebinar that I will be monitoring. So please go ahead, type them into the tool, and I'll make sure they get answered. With that, Mike, I'm going to turn it over to you.
Thank you, Mike. Yeah, this is Mike Holmes with Honeywell Analytics. A pleasure to be here today. As Mike had mentioned, this is the gas detection, basically a 201 series for hosting for by Lesman. We're going to go over, like Mike had mentioned, the agenda here today is basically looking at designing of a gas detection system from a basic stance, which encompasses understand the applications, understand the hazards, whether it's indoor or outdoor, in terms of sensor placement, and then talk about controllers versus PLCs, gas detection selection, in terms of items to consider, and then a couple of examples. We're just going to go over 2 examples, as there's a wide variety of different examples out there. Or applications. So we'll talk about telecommunications and wastewater, and then followed by a question and answer session. So first and foremost, we're going to talk about designing a gas detection system. This particular layout that you see within the image is an indoor style application. We will talk about both indoor and outdoor. As you can see, it could be quite an extensive system, down to even just a few points. So why gas detection? Well, first and foremost, gas detection is a safeguard for life as well as property. It provides early warning to any hazardous conditions, provides opportunity for not only evacuation and notification, as well as from re-entry to that specific area. Providing time for intervention and or correction, basically triggering either ventilation systems, water mist, fire suppressions, or even process shutdown as required. Gas detections themselves, systems, is basically designed, and we'll talk about a little bit more about codes here in a little bit, is to satisfy local fire codes, and as well as provide insurance benefits. There's a couple of things that always comes into play when it comes down to from gas detection itself, is what you're actually looking to address. Is it a real or perceived safety concern? With gas detection, there are recommended practices. There is also required codes, as well as required by law. So understanding the applications, so points to consider. First and foremost, you have to understand the application you're dealing with. From there, you can identify the potential danger points, establish design goals, define the gas characteristics that are going to be within that specific area, provide plant or potential release scenarios. Other elements in selecting a gas system is also, of course, making sure you understand the environment that they're going into, indoors, outdoors, and so on and so forth. And we'll talk more about that in detail here in a little bit. So as you understand the application, the very first foremost is you have to understand your risks. What gases are to be monitored? Are they toxic, combustible, oxygen depletion? What are your exposure limits? The density and properties of the gases itself? What kind of regulations are around that particular application that you're working with? Is it local or federal driven? We'll talk a little bit about Uniform Fire Code, as well as some federal codes for federal regulation, as well as your local fire marshal, all have to be taken into consideration. Unlike fire detection, gas detection is driven more so by industry versus by code. Therefore, it is vitally important to understand your area and the codes within. So we're going to identify the potential danger points. First foremost is basically the release points. Where is the potential leak sources going to come from? Seals, flanges, fittings, welds, expansion joints, and gaskets, engine combustion, storage, loading and unloading areas, runoff areas, and even decomposing materials. And then you also have the receptor points that you have to consider as well when it comes down to protecting people, property, and equipment. First foremost is wind direction, which also includes ventilation systems, again, the runoff areas, confined space areas, and even the communities and facilities surrounding that facility. So you do want to establish design goals when you're actually designing a gas detection system. First foremost, gas detection systems are early warnings of a potential problem. So does your system is your system going to be not only notification or annunciation, basically a method of warning? Is it also going to control ventilation, shut down processes, of course, do evacuations, as well as trigger emergency response? The amount of confinement, basically over pressurization or accumulation of different areas, again, for process shutdown. Runoff distances is basically how far, for example, if a combustible gas were to ignite, how far would you actually go? The amount of congestion or obstacles that are in the way for the gases to migrate to the sensors, the fuel quantities themselves and their mixes, and then of course the margin of safety, the distance between the leak sources as well as the receptors, and then plant safety processes as well as insurance requirements. So gas characteristics, when it comes down to the characteristics of gases, you have to understand first foremost, if it's combustible, is it going to be in the lower explosive limit or the upper explosive limit? Is it a toxicity? Is it toxic-based gases? Every gas itself does have a different vapor density. The density basically can vary with temperature. So cryogenic liquids, as well as flammable liquids, can be impacted by temperature itself. And that's basically for the vapor rate. Lower density gases basically can displace oxygen, such as, or can displace ambient, basically ambient gases. For example, helium and oxygen can be removed from the environment from a gas release itself. Gases under pressure can also condense in an area where basically ventilation would need to be concerned, but it also helps to determine where your point placement is, and we'll talk about that a little bit later. Now, some gases actually form from different compositions, such as dry ice turns into CO2. Toxicity versus flammability, whether the gas itself is going to hydrolyze, such as fluorines in that will actually hydrolyze and actually turn into an acid, based off of the gases or based off the humidities, and then whether the target gas that you're looking at needs to go what's through a pyrolyzer process, which is basically a furnace, a heater, to change its composition to be able to be monitored. With flammabilities, of course, you do have flash points. The lower the temperature at which the liquid can actually form an ignitable mixture that is near the surface, the lower the flash point, the easier that matter will actually ignite. The rate of evaporation, as well as dispersion of the characteristics of the gases, and gas mixes such as any fuels, oxygen, as well as even the ignition sources need to be taken in consideration. And then, of course, if it is an oxygen area, oxygen enrichment environments also comes into play. So basically what we're going to move on here is we're going to start looking at basically profiling a plant and actually potential release scenarios. So gases themselves, the gas sensors themselves, should be placed as close as possible to potential leak sources. Therefore, as part of the profiling of the plant, you need to identify where the physical features are of the plant, identify the ventilation tracts, which way the airflow is going to be moving, identify your escape routes in relation to that, as well as protect entrances to the area to prevent individuals from going into a potential hazardous area. And then, of course, mark your escape routes, and again, identify the wind direction. Other elements to consider is accessibility. Gas detection systems and sensors do not have a finite life. Therefore, they do need to be maintained, and therefore accessibility can play a factor into your design structure. Of course, your wiring and installation comes into play, your environmental conditions, as well as in terms of temperature, humidity, and such. If there's any sources for EMI or RFI, radio interferences, electrical interferences, what your alarm levels are set to be based on your local codes and what have you, as well as exposure limits established by NIOSH, ACGIH, as well as OSHA, for more so from a toxicity stance. And of course, oxygen levels. Some gases themselves, as mentioned, can actually deplete the oxygen. Now, majority of the electrochemical sensors do require minimal oxygen to actually function. When I mean minimal, you're talking roughly about 10%. However, catalytic bead technology does require oxygen to operate at all times. You also need to be aware of any potential poisonings or inhibiting factors that can impact the sensors. So we're going to start into the internal design placement, detector placement from a guideline stance. The detectors themselves, of course, they do have temperature limits, so you do want to make sure that you're within specification. There may be applications to where sample draw or even duct mount configurations may be required. Of course, water, moisture, dust, dirts, and all that, anything that can actually affect or that can affect the performance of the sensor need to be avoided where possible, or increased maintenance to ensure that the operation is complete. Minimize the exposure and protect them from the adverse conditions where possible, which may mean, say, a deluge cover or something of that nature as far as an accessory. Also within the building design itself, the HVAC systems, the characteristics of the potential leaks. Where is that gas going to migrate to is what it comes down to at the end of the day. When monitoring for specific equipment, you do want to place the detectors as close to the leak points as possible. We typically typically recommend is 12 inches roughly from any pumps, seals, tanks, valves, and etc. And then the sensitivity of the detectors, basically, if you do have a little bit further distance that you have to go, you might want to adjust your alarm levels to give you a little bit earlier notification. Then mounting the detector securely and try to avoid vibration, as well as weather protection devices and shields. And the sensor faces should always be set facing downward or within accordance of the actual product itself. If you're talking infrared, it's a little bit different scenario. And if you're on have any doubts whatsoever about the environment itself, doing smoke traces is a great method to determine which way your ventilation is actually going. So indoor spaces, there are very few published guidelines, as well as very few standards, if any, indicating areas, as well as volume effect to be protected from a gas detection. So using UL as a and smoke detectors as an example, it gives you a little bit of better pictorial of what you may require for each individual application. Again, that's a keyword is may. Smoke detectors themselves basically have a 15-foot radius is what the UL code it states for. So guidelines, again, total number of detectors basically really depends on the gas dispersion characteristics as well as air movement, potential leak sources and their locations, as well as the characteristics. Any ignition sources that may be within its path from a wind direction stance or a HVAC stance. Interior space divisions such as walls or other barriers of what may prevent the gas from migrating to the sensor. And then of course, procurement of the product. So again, UL does suggest a 900 square foot ceiling space for each individual smoke detector. I wanted to kind of point this out to you as this is a good guideline that can be used. However, it can get very costly at the same time. Therefore, again, you do need to understand your application much better. So we'll talk about an application that we have up here right now. As you can see in the in the top center, we have a natural gas source. In the bottom right corner, we have a chlorine source. And if you notice to the left of the natural gas, you have ceiling ventilation. So basically, looking at this particular application, I can tell you that the gases, both chlorine and natural gas, will actually migrate to that ceiling ventilation. So therefore, you do need to make sure not only do you have point detectors where the chlorine storage area is and the natural gas source is, but also within that ceiling ventilation. Therefore, you do know if that particular gas vapor is migrating from one location to the other. And then you do have two locations, two doors, two entry points to this facility. So you do want to make sure that you have the proper notifications to prevent people from going in and being exposed to not only the chlorine or natural gas, but also prevent them from even turning on a light switch if you do have a natural gas leak. Now, one of the things I also want to point out, to the left of the lab benches, you do have a storage area. Now, what's in that storage area is also a question. That may be an opportunity for additional detectors. So you do have to look at those kind of hidden areas at the same time. Now, when you do outdoor applications, it's very similar to what you're doing as considering as in the indoors. However, the differential is now instead of a controlled ventilation, now you have to identify the prevailing winds that can prevent the gas vapors to migrate over to the sensor, and also the angle at which the winds come in. Again, smoke traces, if in doubt, that's one of the best ways to do it, and a seasonal approach. We do have information on that. It can be shared on how to do these sort of tests if required. And you can contact Lesman, and we can ensure that this information is shared with you. Orientation of structures, again, the not only structures but terrain can also have an effect on how the gas is migrating to the sensors. The area, proximity, is it a larger area? Are there toxics? Where are the personnel? Where do they work? There's a lot of variables that come into play in potential leak source areas versus where even the people and or equipment that can cause a hazard come into play. Areas you also have to look into is also where entrapment of where the gas vapors are going to migrate to. They could go up into a columns or the low-lying areas, or even into confined spaces. And again, this is all based off of the vapor density, which we'll talk about next. Also identify any potential source ignitions in relation to where that leak potential is. So as discussed in the 101, every gas does have its own unique vapor density. And this is vitally important, not only outdoors, but also indoors when it comes down to sensor placement. The heavier the gas, well, basically, the lighter the gas, it is going to migrate up to the ceiling. So basically, for example, hydrogen will actually migrate up to the ceiling and actually find the little caveats or little holes within. So you do need to pay attention to that, as well as air currents within that area. The heavier the gas, and I apologize for going in opposite, the heavier the gas, it's going to fall to the ground. So we typically recommend about 18 inches above the grade is where you're going to be. The reason for that is you do have a potential in some applications to where you have a liquid spill that will turn into vapor. Therefore, it is important that the detectors be slightly above that to prevent from being submerged. A few other guidelines, basically, when it comes down to actual detector placement. You do want to take a look at the increased grid density, basically used in outdoor, basically for greater potential leak dilutions. Again, dilution is a factor where you want to make sure that the sensors are close, as close as possible to the potential leak from a dilution factor, as well as, again, your wind shifts. When it comes to outdoors, unlike the indoor applications for even smoke, your focus should be, again, is where the leak potential is going to be. This is just a quick base idea of what to look at. So general locations, again, toxic gases and vapors. First, foremost, identify the gas leak and work source. I can't stress that enough, as well as the exit points. Understand where the people are typically working. Placing detectors between them also helps in the work safety. Some other general considerations to also take to take in. Again, allowing access to the sensors for maintenance, for calibration and or replacements. Again, sensors do have a finite life. They do need to be maintained regularly. Understand the local conditions. Is it the vapors lighter or heavier than the air principles themselves? Locate the detectors within their temperature ranges. If you can avoid exposure to the radiant heat, such as even sun beating directly down onto them by using some sort of deluge cover or sunshade, that will significantly help the detector's operation as well as its longevity. Keeping the detectors away from moistures and chemicals, that is you try to do as best to prevent basically your sensor from being attacked, being impacted by variables that are not of the true source. Again, avoid vibration and mechanical shocks where possible. Observe the recommended wiring and tagging practices. And the reason we put in tagging in there is when you do have sensors throughout a facility, if trying to chase one down from an electrical stance without proper tagging can be a difficult process. Use shielded cable. Always use shielded cable. And the reason for that is any potential interferences for radio frequency interferences are eliminated by using shielded cable. So always follow the proper grounding practices. Actually, NFPA 70 does have suggested measures within that, as well as your local electrical codes. And then always observe your detector mounting orientation. Make sure it is within compliance. So a couple little suggestive areas here. We're going to use a tank farm here for a couple examples for outdoors. First foremost, you want to locate where the leak points are, as well as where their ignition points, ignition sources, and so on and so forth, as we discussed. You'll notice in the picture on the left-hand side, we have an X and X with an optima at the top of the tank, which is basically where the fill line is. And because this is a liquid, basically a liquid tank, if this tank were to rupture, it is going to fall down into a dike wall. So therefore, we have actually detectors down within that. As the liquid starts to vaporize, it's going to be approximately 12 to 18 inches above that grade and will actually migrate into the sensing path. This is basically the same application. The differential here is instead of having point detection at the bottom of the in the tank area, we actually have open path detection. And therefore you get complete 360-degree coverage regardless of which way the prevailing winds will go. In a multiple tank area, you may even have a series of 7, 8, 10 tanks. So good guidelines would be actually putting point detection in between the tanks where the tank leak potentials would be, and then do a complete area, complete coverage, 360-degree coverage around the entire area. And there are some different sources that you can actually use to help in identifying and developing combustible gas detection systems. NFPA 52, Instrument Society of America actually has an article on there as well as professional safety engineering firms all take advice into consideration. You can get into some even more unique applications, such as filling stations within railroad, which is basically nothing more than a tank yard, but on wheels. So you would do basically the exact same point. You would actually put the detector up where the filling area is going to be, the point detector, and then you're instead of having complete 360 degree monitoring, you would actually run your accels, your open path, along the railroad track on both sides. Again, part of the things to understand is what are adjacent areas that can also be a potential, whether it be housing, whether it be other facilities that all can be impacted by gas vapors at the same time from a given site. Some of the publications that you can refer to is ICA. They actually have some good recommended practices. I mentioned ACGIH, which basically set up the guidelines, pardon me, in combination with NIOSH for exposure limits for toxicity gases. And of course, NFPA does have some guidelines and practices, as well as OSHA for confined space. Pardon me. Controllers versus PLCs. While there's a lot of verbiage on this slide, I'm not going to talk completely through this, but at the end of the day, controllers and PLC system, program logic controllers, are virtually the same in theory. However, both systems have a unique design purpose around that. Controllers themselves were actually designed with life safety devices in mind, whereas PLCs were designed for plant control operations. While both devices, most devices themselves share the similar signaling inputs and outputs from a design stance, there are a couple of unique differences that come into play when it comes down to this. Again, this is a lot of verbiage here, and will be so I'm condensing it down to quite an input. Sorry. So basically, under process control itself, in most cases, you do have a roughly a 10% input buffering in the design phase itself. So a lot of people do like to use PLCs when it comes down to coming into building a life safety system. However, unlike PLCs, the controllers themselves are actually designed to be very simplistic from a programming stance. So therefore, you do not have to have an individual that is been trained and certified for to program PLC systems. Therefore, your cost of ownership, while the hardware itself may cost a little bit more up front than a PLC system, the actual overall cost when it comes down to programming that becomes actually less than what a PLC system is. And that is because you do have to hire somebody that is required to is educated to be able to program the systems up. Controllers themselves, they do have built-in displays for viewing alarms and faults, where PLCs actually require a computer in addition to its original hardware for the human interface itself. It may also be known as a man-machine interface or even graphical user interface. And many of the PLCs HMI systems do require software package, which are licensed agreements, where controllers, again, it's all built in. Again, just kind of reinforce about the pricing here. Controllers, yes, they do cost a little bit more up front. However, at the end of the day, when it comes down to the physical hardware for a PLC system, its software and the experienced labor, the overall cost of a controller actually becomes much more attractive. Now we'll get into detector selection. Basically, there's a wide variety of gas detection detectors out there. And the detector itself, detectors themselves are designed around specific applications. Again, items you do need to consider not only when for selecting the products is certifications. Every application potentially will have a different certification, so you do need to be very conscious of that. Is it going to be indoors or outdoors? So you need to understand the environmental concerns. Is there corrosive potential exposures for the housings? Is there temperature and humidity? What gas type and its range? What outputs signals are required? Whether it be milliamp, 2-wire, 3-wire, even 4-wire connections. HART communications, foundation field bus, Modbus, are relays required? And then you also look at the accessibility, the interface. Is the unit able to be accessed relatively easy and magnet control is sufficient. Or with new Bluetooth designs with the OELD and the XCL, or I'm sorry, the XRL that are within our portfolios now, which use an actual app, allows for a bit more flexibility for interfacing with the device as well. So a couple of applications we're going to talk about here is first foremost telecommunications or battery rooms. As you can see in the upper left corner is a bank of batteries that are being charged. And the reason for this image itself, because if you look at the right picture, that is actually a battery room that had hydrogen buildup in the ceiling without proper ventilation and caused an explosion. So again, why do we monitor hydrogen within a battery room application? So when you're actually charging batteries, the off gas of a lead acid battery is basically hydrogen, and and as hydrogen builds up, hydrogen itself is explosive at a wide range of actually concentrations, ranging down even to 5% to 95% in the air, depending upon how much dilution factor comes into play. Hydrogen is the lightest of all gases. Therefore, it is going to migrate up into even the smallest pockets of a ceiling or you name it, and actually get itself into that area. So you do need to make sure that you have proper detection within those small areas. And if ventilation fails, you basically need to have your backup source to be able to shut the systems down. IR detection cannot pick up hydrogen, therefore you do need to use catalytic bead technology. Okay. And basically, as mentioned with using the controller along with catalytic bead technology for measuring the LEL, the explosion limits, the controller itself not only will provide indications outside the room to prevent entry, it'll notify the operators of the potential to basically for corrective actions, and potentially even shut off the actual charging system, the UPS, to prevent even further hydrogen buildup. So again, hydrogen is the lightest of all gases, and it will rise up into the peaks. It is colorless and odorless. The detectors themselves should be installed at the highest draft-free location, especially within the battery compartment rooms. The size area of the one detector can, again, depending upon the ceiling structure, possibly even a single or small amount of detectors can be used. It depends on, again, the pockets that it's going to fall into. You do want to measure even its immediate surroundings, and then if the hydrogen detector again accumulate into the small locations, what have you. This is an example of two UPSs. We're using the XCD RFD, which is the remote flammable detector. Have those down at eye view, and then have your actual 705 sensor with a collecting cone at the ceiling level. And the reason for the collecting cone, these accessories are designed for specific purposes. These purposes are, with hydrogen being the lightest of gases, it is going to migrate to the ceiling. As it migrates to the ceiling, if you have a collecting cone, it'll actually focalize the gas into the sensor face and get faster responses. And then, of course, we're tying these back to, for example, in this particular one, with one of our touchpoint plus controllers with an optional horn and strobe directly onto it for notification, and that would be located outside the room. Another application is wastewater treatment. Wastewater itself has a wide variety of different wide variety of different opportunities. In the bottom left picture, actually was an event that occurred just last year within the Chicagoland area, where a wastewater treatment plant in Calumet actually exploded, injuring 10 people. And this was an indoor application. So we're going to cover basically the wastewater treatment process to give you the base idea of some applications here. You have a bar screen room, you have a wet dry well, basically your lift stations. You have a chlorine storage room potentials, which is basically your sanitizing, sludge dewatering, as well as your digester tanks. And then we'll even talk about a couple of products as we go through this, not only from controls, but also transmitters. This here is just basically a overview of the different processes that wastewater treatment goes through in its entire phase cycle. We'll start with the bar room. And basically the bar rooms itself is you're bringing in your waste. And it's basically taking out the large waste. It's the pre-stage of the filtration when it comes down to it. And you do have a potential, because of decomposition of the waste materials, of not only methane, but H2S, oxygen depletion, as well as even CO. The wet dry well lift stations are basically, again, it's by OSHA, it is considered a confined space. Not only do you have H2S as well as a methane buildup, which could cause explosions, as you saw in the previous picture, but you also have a potential of oxygen depletion. A couple of products, both not only the XCD, but even the XNX with the Optima for the methane to reduce in some of your maintenance costs. Chlorine, the chlorine storage rooms. Now, chlorine is not only, there's also some other cleaning agents or sanitary agents now being used. However, we're using chlorine as an example here. So chlorine itself is, again, put into the materials for sanitizing the water that's coming through the wastewater treatment itself. There's a wide variety of different gases that potentially could be released. And we do have a series of different products that can be used. These are typically from a toxic stance, is chlorine, ammonia, maybe ozone, or even chlorine dioxide. And we have a Series 3000, which is basically the a two-wire loop-powered device for toxic gases. But we also have non-class 1 Div 1 areas such as the Satellite XT, which also can measure those gases. Oops. The sludge dewatering process is basically the removal of the water itself from the actual organic material. And again, because of all the decomposition, the decomposing rates and what have you, you have the exact same risks of methane, H2S, oxygen, as well as CO. Then you get into the digester itself, where the sludge is going in, and then it's actually coming back out. These tanks themselves are pulling off the water as well as the gas vapors. These gas vapors then are either sent off to flare, or they may even be sent to back into a different process for combustion of generating electricity for the plant itself, for the wastewater treatment plant itself, or even adjacent areas. Same product mix really comes into play as XCD as well as the Optima for the for lower maintenance. As you can see here, from a gas detector stance, These are typically the ranges that you would come across. I'm just going to pick a couple out of here, such as H2S. It can range anywhere from 0 to 15 to 0 to 50 to 0 to 100 ppm. Again, local codes, not only local codes, but also OSHA and NIOSH and all that do have a factor in these detectable ranges. Therefore, our products are designed to actually meet those applications. And as we went through the entire process here, this is just kind of a chart giving you a base idea of what different detectors, the source is, as well as what gases are within. So, for example, pump station is typically combustible vapor, and you can use the SensePoint XCD or even the Optima Plus.
If you want to know more about the technologies we supply, all of our past webinars are posted both on our website and on our Lesman Instrument Company YouTube channel. You can find those videos there.